Continuing on 711.
I got on the homework for some reason.
Oh, no. Notes. It says notes.
I have my note paper and I finished the homework. I think I'm working notes.
So where we left off
Wait, do I need to turn in my homework?
was talking about EIEIO, right? If you remember that. How EI was being bisected by KT and how EI was perpendicular to KT. This is where we left off.
I printed in my Bible. Can I just start a new paper?
Sure. Whatever.
Oh, no. Wait, should we turn in the chapter 6 homework?
Yeah, if you did not do it last week, go ahead and turn in chapter 6 homework.
Oh, wait. How many should we have? Did I turn in mine? I can't
Sorry,
check.
I'm not spending class that you did, but I'm not spending class time on what should you have. We skipped one of them. That's up to you guys to be keep it organized. We gave you a plan book so you could stay organized. Right? You have a new plan book for this quarter now, right?
Yeah.
Well, I'll take your plan book then,
If you want.
because I do use it.
Miss Smith has
Did they just say if you want a plan book, get it?
Yeah.
They didn't give one to each person. And I have your.
Well, that's because some people have their own.
How was it?
Digging out our bushes was awesome.
Oh yeah, I'm gonna hop up top, and I'm surprised you can't feel them moving around up front though. You could feel them a lot worse out there.
That's because
They'll like scoot. Oh yeah. All right, so in the CPM world of they like to coin certain phrases, expressions, whatever. Their kind of way to set you up thinking through a proof is explore, conjecture, proof. So we want to remember that conjecture, I know we've talked about this multiple times, but what is a conjecture?
kind of like an idea before it's a theory.
Yeah, it's like what you think before you've actually proven it, or it's something that you have yet to like put through the paces of trying to disprove. Once you actually take a conjecture and prove it or disprove it, you know whether it can be a theorem or not. So theorem, by the way, not theory. Theorem is what we've agreed to be true. So we're going to use that technique to try to prove some things about our quadrilaterals. So if we think back to our kite from last week, Kip and his kite, he has these markings, right? Because part of what makes a kite is two pairs of congruent sides that are adjacent to each other, not opposite of each other. And then Kip drew this diagonal. And we have a little bit more on our paper from last week. But if you don't have a kite drawn on your paper, go ahead and draw one real fast. Like, it doesn't have to be perfect, but we're going to label it so it looks appropriate. Now, a hack to drawing your kite is if you have graph paper and you make similar triangles on your graph paper. So if you set this up and you come down and left a certain amount and then come down and right a certain amount, you can nicely kind of build what is a true kite if you use your graph paper. So, come down 3, go out 4, something like that. Do the same on the other side and then just connect down to that center line. And then we said something about the other diagonal last week. This was EI last week. How do you know that? But how do we know that?
Okay, so we know that the one line. So we know that when it's bisected, it's being like split in half. So like you.
How do we know it's bisected?
Because
I mean, we said it was, but we didn't really.
Because you got 3 sides. You got like 2 of the same sides, and then you share the lines.
but I only see one set of sides marked. If we ignore the bottom of the kite, which we don't have anymore, if we look just at the top section.
Okay.
So like my red line is this, right? My red line over there, FH, is here.
So if
David?
if these two triangles are congruent to each other, then we
Yeah.
get that
No, wait,
line.
are they?
Yes.
How do we know?
Side angle. Yeah. No. We can't. Yeah, we can. If they were bisected,
We
then
don't
so it should
know.
be right angle.
We don't know these angles. We don't know.
Side angle, side
How?
angle.
Because
Liang.
Because there's the side, the angle G, and then this reflexive property
For what side?
with GJ.
GJ is equal to itself. So if we try to prove, guys, you will be asked to do this. Not necessarily for a kite, but like you will be asked on a test, like state test, prove the diagonals of a kite are perpendicular. Or prove the one diagonal bisects the other. So this is like, I need you with me actually carrying, because it's okay, like, not it's okay. It's easy to like nod and be like, yeah, yep, I totally would have gotten there on my own. Like, but seriously, think with me. We don't know any of the stuff that we had talked about last week until we can prove these triangles are congruent. To prove these triangles are congruent, we knew these pieces. That's a given from kites, right? If this is a kite, that's given. And then we knew that this diagonal bisected, and we proved that because we proved that this triangle is congruent to this triangle, right? That's how we knew this angle congruent to this angle. So then we have these. All we have to add in is the reflexive, and you have side, angle, side congruence.
Okay, so we know that bisects those things.
Once we know it's side, angle, side, we know this angle is congruent to this angle. Which actually I should do 2 tick because we already did 1 tick there.
So then we also know that those are 90 degrees.
Not 90.
Ooh, we do. Because we know this angle is congruent to this angle, and together they are a linear pair. So if we are flow charting this or 2-columning, this is everything we're going to have to write down. So as much as I know you don't really want to write this down, let's write down the things we need to know, right? So we already had GFE congruent to GHE, right? We're going to say we already had that. We already had these top angles congruent to each other. So what we could say is just by reflexive, GJ is equal to GJ. Then triangle FGJ, so we'd say FGJ is congruent to HGJ by side angle side. Like if you were doing statement reason. Our next one, because of that, we're going to go ahead and shorthand. Angle F is congruent to angle H, even though there are bigger angle F and angle H. We'll assume we're talking about the small ones that we have here in the picture. And also, now I am going to have to write this 3-point angle notation. Angle FJG is congruent to angle HJG. So all we're saying here is that this angle is congruent to this angle. But then we can also say, I'm going to say ditto plus crap. So our reason here was from congruent triangle. So really this is CPCTC. Remember, congruent parts of congruent triangles are congruent. So really, that's all we need. CPCTC. Congruent parts of congruent triangles are congruent. With me, remembering that. How can I say this? That this purple angle and that purple angle equal 180? Linear pair. Right, so FJH is a line. Or FJG plus GJH is a line. Like, or really, I mean, you can just say linear pair. Or you could call it a supplementary pair if you wanted. Because we know FH is a straight line. We drew that diagonal as a straight line. Now that we know that, what else would we need to say before we could prove it's a perpendicular bisector? We already know it, but we need to say it, because if we're going to use it in our proof, we have to say it. If this is a perpendicular bisector, this needs to be equal to this, right? So FJ.
Congruent to HJ.
How do we know that? CPCTC. They're congruent triangles. Once we know the congruent triangles, congruent parts of congruent triangles are congruent. We've got the 90-degree angles. We've got the congruent sides. So if we've got the bisected here, we've got the perpendicular here, we can now say what GE is a perpendicular bisector of FH. That is CONV. You cannot read that. Converse of definition. If we define a perpendicular bisector, it says it's a line that cuts another line in half and makes 90-degree angles. We have found a line that cuts lines in half and makes 90-degree angles. Therefore, it must be a perpendicular bisector. Yeah, converse. CONV. Sorry. I know. It really just looks like COM with a little tail. CONV, converse of. Or I mean, you can really just say definition of perpendicular bisector, because it goes either way. So that's the issue with, like, I want to let us kind of breeze through things kind of easily, but when it comes down to you guys taking the test, I want to make sure that you'll think about, oh, I have to write that down. Like, don't assume it. If you're gonna use it, you have to have it documented. Make sense? So now let's move on to one you haven't had yet. A right trapezoid. Yep. So consecutive angles of a polygon occur at opposite ends of a side of a polygon, meaning that they're neighboring. Right? For example, M and P in the diagram are consecutive, or M and N are consecutive, or, you know, you guys are good enough to figure that out. So what can we figure out about quadrilateral based on consecutive angles? How are M and M related versus M and P versus P and O versus O and P? So let's go ahead and sketch this on our paper. Grab a ruler if you need. But this, I know, this is why we have graph paper. This is the most important part. Make M and P congruent. So really, make this vertical, make those horizontal. That's why we have graph paper.
of the angle inside a trapezoid equal to 70? 36.
Wait, is this like
But
a
if we
rule?
didn't know that,
Is this a principle?
Hmm?
Is this a principle or something that they have to equal 360? Okay.
It's the same as squares.
Okay.
so write a conjecture about what type of quadrilateral has two consecutive right angles. So remember, when we're doing proofs, sometimes we're asked to prove something we already know. It's like we already know this quadrilateral is 360 degrees. But why? What do we know about MN and PO?
They are
Parallel.
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 Because trapezoid parallel sides.
How do we know that?
Because
MN.
they are two right angles, so they'd have to be parallel.
Because if you make the MP into a transversal, then the two things are.
Ooh. So perpendicular transversal. So my transversal is perpendicular to both, right? So my transversal is perpendicular to both. Sorry, my pen keeps dragging. However you want to write it, you write it how you want to, like, but why we know that is these two right angles. So if it's perpendicular to one line, perpendicular to the same line, they're parallel to each other. They're either the same line or parallel lines. All right, so if that's true, what else can we say? So once we have that they are parallel, we can use
Then
rules about parallel lines.
And then NO would
Oh.
also be a transversal if you extended them, and then because of the sum N and O would be
So I didn't know or something.
So
and they'd add to 180.
so angle N plus angle O equal 180. But why?
So if you extended line NO out to be a transversal, along with the parallel lines, then because of like the they're SS angles.
SS.
Same side interior.
So we're gonna write out same side interior of parallel lines. Sorry, this is. My handwriting is really bad today for some reason.
I'd say it was Monday. It's because it's Monday, but it's not.
Well,
Yeah, right.
It's like a horse one.
So then,
Could we say that MP is vertical, but like is perpendicular to
Wait a minute, what if we...
oh, we're there. We're there. We're even proof. I was trying to double check how much we're supposed to prove. So, I mean, kind of. M, N, P, and O, what do we see? So we saw parallel. We saw those are 180. So then if we add all these up, we could say the angles, and we could write them out, but angles sum up to 360. Right, I'm just making sure that we understand why. We didn't even necessarily have to say that. But what type of shape has two parallel bases and other sides that aren't and sums to 360? A what? Trapezoid. So our shape, so we can say M and, hold on, MNOP is a not just trapezoid though, right trapezoid.
Were we trying to prove that?
Because we saw the right angles. These are lessons that I don't really love how they're set up. Here's why we just did what we did. Now we know that when we define something as a right trapezoid, it has these special characteristics of every trapezoid has the parallel bases, right? A right trapezoid also has one transversal creating two 90-degree angles, and the other transversal creating, what are these always going to be? Supplementary, right? So M and P are also supplementary, but we have two right angles and then two angles that will be supplementary to each other. So if you were told angle O, you can figure out angle N by definition of a right trapezoid. Right? Now you can use definition of right trapezoid as your reason for a bunch of things that you could say. Does that make sense? So now we can use this. Some of these explore, conjecture, prove problems, you're going to be like, but why? Like, we're writing down things we already know. It's because then we can use all that stuff in our next proofs. That makes sense, kind of, at least. I know these lessons are a little bit wonky. So, curious question. Carla's like, so wait. Is a rectangle a right trapezoid? What does a trapezoid have to have? Two what?
Separate bases.
Two parallel bases, right? Like,
Yeah.
And then a transversal that creates a supplementary.
transversals that create supplementaries.
But
Since the 90 and 90 are technically supplementary.
yeah.
So yeah.
Well, could you also say that for a square? Oh well, but that's two pairs of parallel sides.
So I guess
Well,
all squares are
rectangles still have two pairs of parallel sides.
So Carla's like, so I think a rectangle can be defined as a right trapezoid, right? She thinks. But at the same time, like we've talked about, rectangle is probably a better name.
Yeah.
What does rectangle infer that right trapezoid doesn't?
A right trapezoid is where the
Sorry,
parallel.
what?
490 angles.
490-degree angles,
Two sets of parallel sides.
and two sets of congruent sides.
2 sets of congruent sides. They're opposite each other, right? Not adjacent to each other. How could we prove this?
Prove that a rectangle must
So at the very bottom of this proof, and now I'm going to start to kind of expect more out of you guys. The very bottom, the thing that we should be saying is quadrilateral or rectangle, if you want to call it, QRST is a parallelogram, right? If we have proved that, then at the end we will say this rectangle is a parallelogram. Take a moment with this. Just write down whatever you think. Order doesn't necessarily matter. So what you put down first, somebody else might put down third.
Like, are we trying to do the proofs of?
You're trying to prove that a rectangle, which a square is also a rectangle, right?
Yeah.
But a rectangle must also be a parallelogram. So we could start with things that we know because we know this. Right? They told us that. So actually, first thing I would start with is your given, which is that this is a rectangle.
I would say that side 2R and side 2.
Couldn't you say? Okay, so since we know it's a rectangle, then we know that the sides are parallel because it's the definition of a rectangle.
Did they give us parallel sides?
But the
Yeah.
definition of a rectangle, definition of rectangle is two pairs of parallel sides.
Yeah, but what Carla knows Carla knows is it has 4 right angles.
She doesn't know.
Well, you could still turn it into a transversal.
So what you guys are saying is 4 right angles cause parallel sides. We have to prove this to Carla.
Okay.
Remember how I just said we're going to be writing down things that you guys are like, come on, we like, what? I warned you, right? Like, I'm honest with you. Athena's like, it doesn't make it any better. She's just smiling this smile of like, this is silly. So she knows they have right angles. So we can say angle Q, angle Q, angle R, angle T, and angle S are all 90, right? Angle Q equals angle R equals angle T equals angle S equals 90 because definition of rectangle. We said it is a rectangle because that's given. What do we know about rectangles? Well, they're rectangles because they're 90 degrees.
Okay, but like,
You guys know what the word erect means, right? To erect a building, to build it straight up. So that's why rectangle is because the base and the height are perfectly perpendicular. That's why it's called a rectangle.
oh, okay.
Yeah, because when you erect a building, you build it straight up. It doesn't. You don't like Leaning Tower of Pisa. Like now, if somebody said we're going to go erect the Leaning Tower of Pisa, that would mean straighten it. Yeah, and you're all 8th graders, and your brains are in the gutter, and you're like, haha, tee hee hee, erect. But that's not what we're talking about here.
Why did you point it out?
Because my wife used to teach sex. It's not like it's not a big. I know when I say those words,
You know
your
what?
brain is like.
Last year, I
I'm
remember.
pretty sure if
Like,
you didn't point it out, I would have never thought about
I just
So-
remember Mr. Essex going last year. Y'all are not ready for sex ed. Like he would say
And you
that.
probably couldn't even hear him say sex ed without reacting. Is my bet.
Yeah, probably.
So we know those angles are right. What do we know because of that?
They equal 360.
They're parallel.
What?
Yeah.
I thought we were
Keep
trying
going.
to prove that they're
They're
parallel.
like a parallel because they can make a you can have the same side interior angles because they have 20.
Here's how the book kind of phrases that reason. Same side, what do they say, perpendicular angles? Right, same side angles supplementary.
Not a straight line on graph
No.
paper. Just don't.
Same side angles supplementary leads to parallel. When you see same side supplementary angles off a transversal, and we're like assuming off a transversal here, that creates QT being parallel to RL, the bit. And QR parallel to TS. Same side angles supplementary leads to, that's what this symbol kind of means. It causes, it creates, it leads to parallel lines.
And then wouldn't we be at a parallel now?
Yep, now we're at a parallelogram.
Oh my. Yay.
So then don't we just state that QRTS is a parallelogram?
QRFT now, actually. Oh, wait a minute.
Wait.
Nah,
Should you do the same thing that you set up there, or does it?
not mad.
Because you said QRTS.
Yeah, I was making it more complicated than we needed to. So really all you have to type is definition of parallelogram. We technically are, like, we built the definition of a parallelogram to have a parallelogram. Normally when we use this, we're claiming something is true because this is a parallelogram. But what we're doing here is flipping that around and saying this is a parallelogram because the somethings that are true. Does that make sense? So, if then statements, right? On your paper, go ahead and write if, then. This is what we call a conditional. This is what we call a conditional. Now the fun thing about if-then conditionals is if a definition is actually a good definition, this is really funny actually, in your eyes. If a definition is truly a good definition, then these items are exchangeable. So if these items are exchangeable, then that definition is a really good definition. Did you see what I just did there? So if, like, trust me, if ABC is a triangle, then angle A plus angle B plus angle C equals 180, right?
You could switch.
If
Okay.
angle A plus angle B plus angle C equal 180 in a polygon, right? We have to say they're connected. Then ABC is a triangle. Is that still true? So it's true. Either way I switch these. A good conditional and a like 100% true conditional should be able to switch places.
Oh, okay.
Is that what you're doing this in the review videos where we kept having to...
I think those are really stupid because those are really easy.
But a lot of people will try to use conditionals wrong. So conditionals are what we're using in proofs. So when we go to build a theorem is just a bunch of if-then statements put together. If this transversal cuts through two parallel lines, then the same side interior angles will be supplementary, right? If an object is a quadrilateral, then the angles inside must equal 360. If, like, are you with me? I probably don't need to do more. So we are now, and we have been, but we're now formalizing it, going to use conditionals to be able to flip things around and say, well, if we know this, if blank, then that, then flip it and say, if that, then blank. Does that make sense? So we've got like 5 minutes left. You started on your homework last week, and I know it's a big homework. Do you have any questions that you want to go over here? You finished all the way to like 22?
Yeah. I had 3 days.
What, dude, it's still your homework today, so that doesn't quite count.
So that
It's a
means I got-
multiple day homework.
I was wondering...
You're done with today's homework then. If you're done with this, you're done.
It's because I had AO and I did like half of it, and then I used to rest class.
Yeah, I mean, at that point, you might as well just take your stuff, probably. I mean, you don't have to, but we're leaving in like 4 minutes.
Okay.
Leanne's like,
You'll just walk back and forth.
Will we ever use these things ever again? Like, just out of my brain. No, not
Yeah.
this, but
this, okay. So, Athena, I get your 8th grade, like, mindset negative, I'm going to be a poo-poo head because I want to be. But, true story, like, me, real, not teacher hat, like me as just real adult, the thinking that we're encouraging you to be able to, like, process through, that's what we care about. Are you going to use 2-column proofs out in the real world? No. But will you need to be able to defend an argument or defend a stance or like something you're presenting with like reasoning to say, we did this because of that, then we did this because of that, and if this, then that, which allowed us to like this sort of thinking.
the question is math the most efficient way to teach people that?
Pretty much, because it's process-based. It's black and white. There is a right answer at the
The
end.
thing
of it.
is, once you start to get into the gray areas, it's real confusing.
Well, there's a gray area, but there's a black and white like conclusion, right? It either is a triangle or is not. Either is a parallelogram
That's
or
probably
not.
why they said math would be so
ever again. So are we ever going to use these in like